Well folks, Sean here from SMD Methods. You're very welcome into this video. This is the third in the series looking at the front wing of a Formula Student Car application. The last video finished off with altering parameters that were developed during the first video, which was the establishment of the flow field geometry within ANSYS Design Modeler. So in this video I'm going to proceed on and we're going to mesh that flow domain. Then from that subsequently obviously we'll take it on a grid convergence index study for mesh independence, and then into further assessments of other elements for that front wing. So what I'll do is I'm going to jump straight on into Workbench, and let's just open up our project that I had saved. It would have been helpful if this was open before I started the video, but you can't have it every way. The geometry and the meshing has been completed. Parameter set has been established, and this I believe was the last screen that we had looked at in the last video. What I'm going to do is I'm going to change that from height trailing edge to Y, right, just for a Y dimension for a height trailing edge of the main element, YTE trailing edge ME main element. And what I'm going to do is I'm going to put in a new I'll add in a new parameter for X trailing edge, because it'll also be helpful to know what point in that flow field that my trailing edge is. Not only is that this one here was really that I could confirm that I didn't go over the 250mm Formula Student regulation for a front arrow element, but when I have detail on the X and the Y, I suppose what it can give me is a point from which I could relate the leading edge of my first flap, for instance. So what I'll do is I'll copy this, Control C. I'm going to enter in a new parameter, X underscore TE underscore main element. And what we'll do is we'll give that expression, which is the same as the expression for Y, except that it has nothing to do with track height. So I'm going to, or my ride height. So I just took off that there, P7, and it's not the sine component, but the cosine component of the angle of attack, and that there gives me my new dimension, 531.259 millimeters downstream from the leading edge, which makes sense. It's a 550mm chord length airfoil, and at zero angle of attack we would find that this should come out to be 550mm, and at 15 degrees angle of attack, obviously along the cosine component, the leading edge and the trailing edge are getting shorter, so I'm down to 531mm. Yep, so I'm going to keep it at that. Now the other thing that I thought of in my geometry that I might try to change, or that not that I might try to change, that I will change. I was thinking about it after the way we split up our flow domain. Obviously, I have one big surface here, and one big surface, and that big surface has had face split operations done on it. So it's the same surface. I've just split the face of the surface. So there should be no problem, because of the same surface, of different meshing at these interfaces lining up, and going node to node effectively. I'm not going to have that same kind of smoothness running here, because this is one surface and that's a different surface, which can be seen here, a buffer region and then a flow field, two separate surfaces. If I mesh that with one, I mesh that with the other. We're not gonna, without having a connection region or without specifying it, and even with shared topology, sometimes it doesn't come out right. What I'm going to do, this line body, actually I should have had that off. I'm going to suppress that because that has nothing to do with my physics. But the buffer region and the flow field, so you can see it down here. If I select one of them, see their shared topology method automatic on or off, edge joints, imprints, none. Leave it automatic. The software will suss it out. But what you can always do is I can make, if I select the two of them, I could form a new part. And once they're seen that they are two surfaces, yes, but they're the same part, the solver then, or the meshing operation will mesh them as if it was a single part. So I'm going to form a new part here, and let's just rename that as what have I called other things? I've flow domain there. I don't know, do I have anything called flow field? No, nothing called flow field. So that is my total flow field made up of two surfaces, the buffer region and the actual flow field surface. So let me just rename that flow field, go for total flow field, because I don't want it to confuse the part with the surface. Total flow field, we call it flow domain. That's what we call the plane there. But anyway, I think that should work all right. Let's just generate everything, make sure everything looks okay. And yeah, let's see how we go with that. There's a couple of things to tidy up before we go into meshing. So just come out. There we go. And let's open up our meshing. Always check your properties just to see is there anything that you could speed up by pre-selecting here. There's nothing on it. Reconfirm my units are in millimeters. That looks okay. And let's select mesh. Now what I need to do is I need to look after my inflation layers here as well, because I'm going to do an unmapped mesh. I'm going to put in inflation layers in around that surface. So I need to know what my first cell height is going to be. I do predict that I'm going to run with a K omega, an SST K omega model, which has a target Y plus value of 1. So with the Y plus value of 1, and also knowing the likes of my free stream velocity, my chord length, my growth rates, and so on, I don't even think I really need the growth rates. That's for boundary layer height. My dynamic viscosity, I can work out what my first cell heights to be. So I'll do a wee bit. We'll put in a wee bit of mesh in here first. And then we'll calculate out what our first cell height is going to be according to the Y plus, our target Y plus. Then we'll come back and we'll add in our inflation layer. So there's a mesh. What I'll do is my sizing and mesh growth, default growth rate, feature size. All right, so okay. Capture proximity, that's all fine. Right, I'm going to put in a default size here, 72. Usually, I take things up in sixes, so I do 6, 12, 18, 24, so on. It's just, I was fond of 8 for a while. I've got fond of 6 now. So this is what we're going to do. Right, so I'm going to go to Mesh, Insert, Sizing. I'm going to F2 this and call this sizing for the far field. I'm going to Control C that just so I can copy on my next sizings. Sizing for the far geometry selection is out there in the far field. Face, apply, element size, let's keep it at 72. I'm going to make that a parameter because when I do my grid convergence index study, I'll want to refine these down, even though with a 72, knowing that I'm going to be refining these down by a factor of 3 or 4 from kind of stage to stage as I approach the airfoil, I'm going to be dealing with a very resolved mesh, a very fine mesh at the outset. The reason for that is not because of grid convergence, grid independence, which obviously is a major requirement in CFD, but it's because me knowing that I'm going to alter my geometry and the way I'm going to alter it is going to have skewing effects on the mesh that I need to keep that very, very fine. So outside the fineness required for mesh independence, I also have a fineness required to allow parametric, parameter-driven sketching, geometry alterations, especially over very small angles. So we'll see how we go with that. Everything else is fine on that. Mesh, right-click, insert, sizing. Sizing F2, Control V, and we'll go for midfield here. Geometry is in here, apply element size. So on 72, I could drop that down. Say if we drop that down by a factor of 4, that would take me down to 18. So I'm not really that worried about massive jumps. I'd like to always keep it from 3s max, but 4 is fine out here where we're going to be going with 2 relatively coarse meshes, where the next one I'll choose maybe to bring that down to 6, or I probably could get away with taking that down by 4 again. See how we go. Element size 18, the feature size, all looking okay. All right, mesh, right click, insert, sizing F2, Control V, and nearfield. Geometry selection, inside, apply. Now, this one was, my parameter is at 18. Now if I bring that down by 4, I'd go down to 4.5. I'm going to bring it down by 4, maybe. I'm breaking my own rules a lot here. Well, let's go for it. And because I want to keep, no, I'll tell you what I'm going to do. I'm going to keep that, I want to keep that, I'll bring that down even to, I'm going to bring that to 3. Because this, why, I'm a wee bit all over the place here, so I'm going to try to just stop and explain myself. When I rotate this, when I maybe stretch this in or stretch that out, I'm going to be stretching this out into cells, and when I rotate this, I'm going to be rotating this in against cells. That's going to skew them cells. It's going to throw the orthogonality off of them. The larger they are, the less likely the software might be for regenerating some of them cells, and it'll just, the skewness will go up. Whereas if they're small, I might get a brand new mesh, because I will be making small increments of maybe ½ degrees. Then when I come in to remesh it, I want to make sure that a new mesh is generated in places where mesh elements are being put where there is no mesh elements. If they're too big, the software might just squeeze the mesh elements a wee bit. So I want to make that very well resolved there, 3 mil, and I try it at 3 mil and see how we go. But what I'm going to do, I'm going to take that parameter off, and that's going up to 6. So what I'm going to want to do is I'm going to want to have a knock-on effect. I'll bring this one up to 12 here then. 12, and then this one, I can't really let that go up by 6. It's a wee bit heavy. It's not too bad. I'll bring it to 60. I'll go up by 5 and see how we go. Obviously, the more elements I put in this, the more computational effort I'm going to see. It's not really what I want, is additional computational effort, but you can't, you get nothing for nothing. We're going to have to use the computational effort if we want to have the ability to be able to resolve these over small increments. Now, what I'm saying is, if we wanted to change the angle of attack by 2 degrees every time, yeah, we can get away likely with a much more coarser meshing through this. But if you're looking only at ½ degree increments, need to be careful for that. All right, let's go for the next one. Mesh, insert sizing. Just going to hit my surface here just to make sure I'm in there. Apply. F2, Control V, sizing. I believe this was called the buffer region. Just call it sizing for the buffer, and I'm going to bring this down to 1 mil. That's very, very heavily. There's a lot of elements in there, so I'll probably be over 500,000 elements over this flow field. That say I wouldn't be too far off it, but let's see what it comes out in. Mesh insert. Now let's put in a face meshing. So you can do this here using face meshing or method. I prefer to use face meshing on this geometry. I'm going to go to surface faces and go for 1, 2. So I'm just controlling button and selecting. Apply 4 faces. Right? Map mesh, no. Method triangles. Best split. That's what I'm going to run with there. Finally, now what I want to do is I want to put in my inflation layers. So for the inflation layers, I'm going to go back to MATLAB, and I'm going to leverage this function that I wrote in the series on the front wing considerations for the STEM racing car application. So again, if you haven't seen it, you're interested in that, go on ahead and look for it. In fact, I think I actually put that function in the chat for one of them videos, so definitely go back and have a look at it if it's something new. I'm going to go for help y plus just to see what I need to put in. So this results y plus, I always write that in the comments of the not this, but I always write in the comments of the functions I create the formula, or how you call the function itself, so you can very easily control C it, and then you can see all the input variables that I want on it. I should have wrote in here the comments as well for the outputs, but I have it I have them compiled in a vector called results, and then the function will list the results out as per Reynolds number, I think it was, wall shear stress. Certainly your first layer cell height, and how many layers you need in your inflation layer to cover a particular growth rate given the first layer height. So that's what I'm going to run. I'm going to go to a new live script, V, Control V, and I'm going to just paste that in there. Now what I need to do is I need to write my variable. So U is equal to, so this is my free stream velocity. So I haven't dealt with this just yet. I'm going to go with, again, I deal in what we call here old money, which is in miles per hour as opposed to kilometers per hour. So we could probably run anywhere from 40 up to 50 mile an hour. Now, obviously the cars are going to exceed that on track, hopefully, safely. However, where we're looking to take a lot of these corners, I need to question myself on what is the speed that I'm looking to generate this downforce at. It's not at them high speeds. I am interested in the downforce and generating them high speeds, but that isn't where I'm looking to generate lap time. I'm losing lap time there. Where I'm looking to generate lap time is the application of downforce on corners taken at particular speeds. So we need to decide what speed we're going at. Now, really, that should be taken from a lap time simulation, or maybe something that's been run in Simscape or in MATLAB, simulate whatever it may be, and just to get an idea of what of your cornering potential, what likely you're going to take these corners at. So if we were to run with a let's see if we went for 50 mile an hour, seems a wee bit heavy, maybe 50. Let's try 45, see where that takes us. So 45 mile an hour, if I multiply by 8, I divide by 5, that takes me into kilometers per hour, 72 kilometers per hour. Let's multiply that then by 1,000, and let's divide then by 3,600. We're at 20 meters per second. Let's try 20 meters per second, 45 mile an hour. I'm going to take it down to 18. I'm just going to slow it up a wee bit. 18 row. Let's go for 1.2. That's of course kilograms per cubic meter. Mu is my dynamic viscosity, which is 1.8 roughly. E to the power minus 5 Pascal seconds. L is my chord length, so this particular airfoil is 550 mil, which is 0.55 meters. Y plus is my target. Y plus value is 1. Going for that because of my turbulence model, my chosen turbulence model. And R is the R is my growth rate. Go for 1.2. That means from if my first cell height is 1, my second cell height is going to be 1.2, and so on. 1.44, and away on we go. Right, so then I'm going to run results. Let's run that, and here we are. So there's my results. Is this the structure that I wrote into the code? Gives me Reynolds number, wall shear stress, a wall distance, a delta, and the number of layers. So delta as well, that's an interesting parameter there. That means my my boundary layer height is 14 millimeters. It's fairly hefty of a boundary layer height. That's fairly hefty of a boundary layer height, I must say, on a 550 millimeter wing at 18 meters a second. There we have it. I would just need to actually check that just to make sure that isn't returning me anything in millimeters, albeit everything should be in meters. Yeah, I suppose I have to say in meters because 14 looks large for millimeters. 0.014 millimeters will be too small. So yeah, I'm assuming this is going to stay in meters. Don't assume anything, but here I wrote this function, so it's in the back of the head there somewhere. So for my inflation layer, my first cell height for the inflation layer running with that value there in millimeters, because that's what we're writing in here. So mesh, let's go on ahead, insert and inflation, geometry selection. I'm going to run out here, so I'm going to build my inflation layer on that surface. That's really what that means. Boundary scoping method is to select that edge, but I'm not going to bother selecting the edge. I'm going to do name selection. Select my boundary, which is the wall of the main element, ME. not smooth transition, but not total thickness, first layer thickness, first layer height. It's just what I copied out of MATLAB, but I'm going to change that into millimeters. Maximum amount of layers, let's double check that again, I think it was 24. Let's double check. Yes, N was 24. The growth rate that generated them 24 layers I had entered in was 1.2. So that's that. Okay, mesh. That's it, as Samuel L. Jackson says, it's time to hold on to your butts, and let's generate this and see what it does. Hopefully we're not going to get any sort of errors. My main concern is this pinching here. If I have a 14mm boundary layer, I'm very concerned that that boundary layer might run out of that surface that is being built into and into this near field surface, both there and also down here, just at the underside of the underside of the airfoil. These are massively small cell elements now, so it could take a little bit of time to get this to mesh. But as I said, you can't get nothing for nothing. If you want to be able to have this provision that we can move and adjust to these levels, we're going to have to pay the tax that is time and computational effort to get it done. So it is ticking away there for itself. But what I'll do is I'll pause the video here and let it do its thing. We are at 13:41. It's given here. I'm going to pause it and we'll sit and I'll watch this because I don't think it should take more than a few minutes. And then we'll come back whenever it's meshed, and hopefully it'll not be much past 13:42, which we're at now. And there we are, 13:42. It did work. No undue, some boundaries of protected topologies have been featured. Okay, we could live with that. What I was really worried about was that we were going to get a problem at these boundaries. Right, so let's have a wee look. First, we could see there that from the near field into the midfield region, we have node to node connection, so our mesh is good. We need to make sure we have that here as well before we go any further, which we do. All right. Everything looks to be connected there. So that was achieved by virtue of the fact that we created a part from them two surfaces. Now, this is where I want to check. So there's our boundary layer. Right. Now, we have a couple of nice little tight enough 1mm buffer mesh elements, cells there between the top of the inflation layer and our midfield region, which is grand. Have a wee bit of scope to move, and I'm at the maximum angle of attack that I'm going to run this main element at 15 degrees. I'm not going to pull it up anymore. I'm more likely to drop it down, and then if I won't need more angle of attack, that's what I'm going to rely on the flaps for. So this relationship should always be the same, right? Because every time I rotate, I'm going to rotate my buffer and this inflation layer together, because what I'm really looking to try to do, everybody, is I'm looking to protect this inflation layer. Right? You know, it seems very skewy there, but that's what you're going to get when you're coming into the point. I want to protect that inflation layer so that when I rotate it, I should be rotating the inflation layer, them cells on the boundary. But now, and I would have been otherwise rotating them into all them triangles, and they would have skewed more potentially, especially at that trailing edge. But now, the whole lot of this snapshot, if I just took that there, that's always going to look the same for all angles of attack. Like the relationship between that cell and this cell is always going to be like that. That cell and that cell and that cell and that cell and these two are always going to look like that. There's going to be no morphing there. Where the changes are going to happen is going to be out here, which admittedly is tight to that, and out here. Not in here. These are all going to be rotated. That whole entire mesh is going to be rotated together. That's the theory. So we'll see how we go on that. But let's parameterize. I have a parameter in for that, parameter in for that, parameter, face mesh and fine inflation. I don't think I'm going to change. Let me see. I will. I'm going to change my first layer height and I'm going to leave them as parameters, because when I copy and paste this and I start bringing in flaps, my main element, my ME, is going to shorten. and then my flaps are going to take on their own. So I want to be able to change these from outside the software. Okay, and then mesh, what I'm going to do is I'm also going to take account of how many elements I have. So I do have a way past the 500,000. I thought I was going to run up till 818,550. Awful lot there. So it's heavy. I definitely could reduce what's happening out here big time. You know, there's no need for running at that dense there. This is all good and that's okay. I don't mind that so much. But I could probably let them grow a wee bit better into there. There's plenty of scope for them to grow. Anyway, that's it. You live it and you learn. So that is our meshing done. What I'm now going to do is click update and hopefully see a wee box appear here to say that the meshing, translation to Fluent was successful. So that all looks good. All right. Let's close down out of this. Let's hit save, and then I'm going to stop this video and try to keep these more bite size than video 1, which I note has gone on for over an hour. So video 3 here will very unusually be less than half an hour. So we'll stop it there. We'll come back into the next video when we will focus on the setup of the solver, which will be Fluent, and see can we get some results out of it. Okay, so thanks very much for joining me in this video. I hope to see you in the next one. Good luck.